to register.
No, I said no registering. So we can joke a little bit.
Of course, we can start, hopefully, to restart our work. And despite of all technical problems, we continue with the next talk. It's really pleasure for me to present Valeria Banica from Sorbonne University. She will have joint work with Luis Vega, and she will speak about growth of the energy for the binormal flow and the Schrödinger map. Please, Valeria.
Okay, thank you, Vladimir. And I want to thank all the organizer for this very nice invitation. And I want to say that I appreciate your effort for doing in-person meeting. I think it's very nice and important for everybody to have in-person meeting, and then all the effort you put to transform it also in hybrid mode, which is always difficult. Okay, so thank you for all this. And well, as Vladimir said, it is a joint work with Luis Vega that we'll present. So I guess many of you have seen talks about these topics of the binormal flow, but each time we have also new results. So this is a recent one from April, I think. Yeah, from April. So it is about the growth of the energy, and it is for the binormal flow and the Schrödinger map. So do you see the mouse on the slides? Do you see the mouse or not? My pointer.
Yes.
Okay, great, thank you. Okay, so there are not, forget about this. This is, there will be just 14 slides. Okay, so the plan of the talk is that I will recall a bit the equations that I will study. So actually there will be 3 equations, one of which you are very familiar with, another one, and this one which you are less familiar. But in any case, as we will see, there are a rigorous connection, explicit connection between the 3 equations. So it is working with one can help you understand things about the other 2 also. Okay, so it's very nice to see them all, the 3 of them. And precisely the game we play with Luis, that is that we get information at the level of the cubic NLS and we transport it at the level of the binormal flow equation. But even at the level of the NLS, the result can be interesting also. Okay, so the result, it will be about growth of density energy for these equations. And in the last 4 slides, I will, if I have time, I will give some. So let's go first. About the equation. So the binormal flow, I will just put a slide about its motivation. It appears as a model for one vortex filament dynamics in a 3D fluid. By vortex filament, I mean where vorticity is very large and located, concentrated along a curve in R3, and as the fluid moves, it is expected that the vorticity remains also still concentrated along a curve in R3 that evolves in time. So the question is, how is this curve evolving? So it is a question about evolution of curves in R3. Okay, it is the oldest one. It goes back to Dario's work under the supervision of Levi-Civita in the beginning of last century. It's a very simple equation and very rich because eventually also that it is connected to the 1D cubic NLS, which is a very rich equation. And it is for the moment a formally derived model for this physical problem. And the formal derivation is quite easy. You suppose that the vorticity is concentrated along a curve that I will denote by chi at time And then you use the Biot-Savart law, and eventually, after some manipulation, you end up with this equation for the curve. So the curve evolves by this law. This is a vector, this is a vector, the product is a vector. So it gives you the right-hand side, gives the direction in which the velocity goes. Okay, so this is only for validation. Nevertheless, the last breakthrough in the direction of proving this conjecture that it really happens, that you have something like that, is to Gerard and Christian Seyss a few years ago. And roughly, it is an if theorem that precisely if you suppose that you have this conservation of localization of the vorticity on a curve, then under other niche, that your curve satisfies precisely this equation. Now you can note also that if you change your curve, you take a solution of this equation, so it is a curve, and you can rescale it to be arc length parameter, so that the denominator here is 1 to the power 3, so 1. You end up with a simpler formula, which is only that chi t equals chi x. X is the arc length parameter times psi xx. Okay, so it is an equation for an evolution of curve in R3. And I have to say also that there is activity around this kind of problems lately, understanding how vortex filament evolve. There is a result of Bedrosian, Germain, and Harold Griffiths for not for Euler, but for Navier-Stokes, so it regularized the equation. For Euler, you have particular cases of evolution of vortex filament, as for instance, Davila, Del Pino, Nuss, and Way show for helices. But helices means that you have, so here is 3D Euler, but restricting to this kind of vortex filament gives you a reduction. So you're not really in 3D or less than 3D in some sense. So that's why they managed to do it. And last but not the least, Bob Gerard and Didier Smets proved that for superfluids, this, a linearized version of this equation is valid for the evolution of vortex filament in fluid that are curves in R3, right, in space, that have the same direction as plus and minus infinity of their arc length parameter. Okay, so this is the state of the art at the level of fluid dynamics and about deriving rigorously this model. And from now on, I will consider this model and just work on it, and everything will be rigorous starting from now. Okay, so, oops, sorry. Okay, so now I will explain how, considering first the binormal flow, you end up to the Schrödinger map and then to the 1D cubic NRS. To end up to the Schrödinger map is very simple. So if you consider an arc length parameterized solution of the binormal flow, so the equation is this. You can note by using a Frenet system for curves in S3 that this is the tangent, and we are taking the product with the derivative of the tangent. So derivative of the tangent is curvature times the normal vectors, and tangent times the normal vector is the binormal vector. So that's why the equation is called the binormal flow, because what the law says that the curve evolves in the direction of its binormal at the point you look at times the curvature at that point. Okay, so you forget about this for a moment. And then if you consider just the tangent vector, so the derivative of the curve with respect to the arc length parameter, On the left, you'll have the evolution of the tangent vector. And on the right, if you differentiate this, when the derivative falls in here, you have the product of two identical vectors, so it is 0. And when it falls in here, you end up with t times txx, which is precisely the 1D Schrödinger map with values in S2. Why in S2? Because we said that we took the arc length parametrization. So the derivative of the curve is of modulus 1. Okay, so the passage from the binormal flow to the Schrödinger map is quite trivial. Okay. Okay, now how to pass from the now to the 1D cubic NLS. So this is due to Hashimoto in the 70s, and it goes. I will present it in the following way. Instead of using the Frenet system that completes you the tangent vector with the binormal and the normal to get a frame of R3. Instead, for the tangent vector, you complete it with two other vectors to get a frame of R3, such that these two other vectors, their variation are only in the direction of the tangent vector, which this frame eventually, so tangent vector E1 and E2 is called the parallel transport frame. Okay, you can always do this. So if you have a curve, or you have the tangent, and then you can complete like this to these parallel frames. And then, so this is valid for all time and space. So this coefficient, you take the two of them and you construct this complex function. And then you do a lengthy but not too lengthy computation, and you end up that if initially your curve satisfies the binormal flow, then this function, this complex function, satisfies the 1D cubic NLS. Okay, actually Hashimoto, when he wrote the paper, he also introduced, instead of considering this function obtained by considering this parallel frame, you can consider the Frenet system and then consider therefore the curvature and torsion and construct a function in terms of curvature times exponential of something in terms of the torsion, which is exactly like in the Madeleine transform. But of course, you can have issues with the Frenet frame when the curvature is 0, for instance, or such things as you have from Madeleine when you have the amplitude 0. But in here, you see, you just use these new frames, and then you have no problem of defining everything, which is very nice. So this is the passage from the binomial flow to the 1D cubic NLS. Now, what's happening is that we don't have too much information about the binormal flow, but we have information about the 1D cubic NLS. So we want to play the game the other way around. We have to understand if starting for the 1D cubic NLS, we can get a solution of the binormal flow. And this is possible. This is also the work of Hashimoto. And it goes the following. If you start with a smooth solution of the 1D cubic NLS, with some linear term in here that eventually I will show that it is not important, so don't think too much about this. It could be 0, for instance, to simplify and get the pure 1D cubic NLS. And if you get you fix a point at R3 and a frame and the time, initial time and initial arc length parameter, you can construct a binormal flow solution imposing what the tangent vector and the complexified vectors in the parallel frame should satisfy if you are a solution of the binormal flow. Okay, so I won't enter too much into detail, but eventually it is known that if you have a smooth solution of the 1D cubic NLS, you can construct a solution of the binormal flow such that its tangent and its complexified normal vector satisfy this system. Okay, so you can take it as a black box. Okay, you know that the tangent will satisfy this, the normal vector will satisfy this, and also you have an equation for the derivative in time. Okay. However, okay, yeah, I wanted to say that A of t is not important here. Why? If you have a solution for this equation, of course, you can have a solution of the 1D cubic NLS by removing this part, which depends because the coefficient here depends just on time. So you can remove it by a time-dependent phase. And if you do this, so if you start with a solution without this A of t, okay, so you have to add this extra factor. If you do the recipe here, then what you will construct is the same thing as you constructed before, except the normal vector, they are shifted in the plane orthogonal to t. So forget about them. Constructing a curve, it is enough to have, it is determined by its tangent vector. So the tangent vector doesn't change if you multiply your solution. Yes? Yes?
May just check in your computer, you can see the full screen, also the last bottom line, because we have just a bit of difficulty with the last.
I can see it.
You can see.
Do you see A of t is not important or not?
Yes, but not describing.
Oh, okay. So I'll read it. Oops, I don't know how. I mean, on my screen I can see.
Well. Okay. So we will fix.
Okay, I'll say. Okay, so okay, so in any way. Okay.
Don't worry.
Okay, I'll read it in any case. I'll read it loud.
You can go in full screen, or you're already.
No, I'm not in full screen, but I can go in full screen if you want.
Yes,
let me see. Yeah. Blah, blah. So is it better? I'm full screen now.
Okay, it's not a problem. Okay, you can go. It's not a problem. We're fixing. Thank you.
We will fix it later. Thank you.
Okay, so I can exit the full screen, or because full screen is huge for me.
Yeah. You get to which as you prefer.
Okay. Sorry. Okay, so what I was saying is that this coefficient here doesn't matter. Okay, because by this recipe you end up constructing the same curve. And what is written on the last line is that describing the curve geometrically might be difficult. In which sense? In the sense that if you want to understand how it looks like, you have to understand its curvature and torsion roughly. So you have to have pointwise information about the Schrödinger equation, the solution you have. Moreover, I have to point out also the fact that the way that the solution of the NLS equation that you have initially enter the way you construct the tangent and the normal vector, it's non-trivial, it's not linear. You see, you have, I mean, given yourself the function u, the system for t and n is linear in n and t. But if you think in terms of little u, here you have a quadratic power. Okay, so the passage from the Schrödinger solution to the tangent and normal vector, it's quite intricate. Okay, typically you have well-boundedness for NLS in L2, right? But it is not for that you can get well-posedness for Schrödinger in H1. Okay, there is morally one derivative between the two of them, because the tangent vector and the normal vector at some level, and it's when you differentiate them that you end up to the curvature and torsion. So morally, you have decalage, well, a gap of one derivative between them But this is not enough to get, if you have information here in L2, you won't get information for the Schrödinger map in H1, for instance. It is precisely because in here you have this quadratic power, so it's not linear, it's not simple, the passage. Also, all this works when U is small, this constant, okay, because you want to integrate this. And the issue, and I mean, this from now on, I will work with a singular solution, I mean, with solution of NLS that develop of singularity in finite time that are smooth before the singularity, such that you can construct a solution of the binormal flow. And then you will look at the limit of the solution of the binormal flow when you approach the time of singularity for NLS. And since the binormal flow solution leaves two derivatives before NLS, you have more chances to get a nice result at the level of NLS, even if at the level of the Schrödinger things are getting very bad, right? Because from chi to from the binormal flow to pass to the Schrödinger map, you differentiate once, and to pass from the tangent from the frame of the curve to the cubic NLS solution, which roughly is curvature and torsion, you have to differentiate once. So from passing from here to here is morally differentiating twice in X. Okay. Okay. So what about singular solutions? So this is a table with what we have. What we know for the moment about some solution of the binormal flow that generates corner in finite time. So these are the results at the level of the binormal flow. As we'll see, a corner, generating a corner here for the binormal flow would mean that the NLS solution generated Dirac mass. And we have also to have in mind experiment in fluid that fit with the shape of the curves we found at the level of the binormal flow. So the oldest results are about the self-similar solution of the binormal flow, which are known by physicists since the 80s. But rigorously, mathematically, what's happening at the time of singularity was studied by Gutierrez, Rivas, and Vega. And the level of NLS, the corresponding NLS solution is that just the fundamental solution with some coefficient in front. You have a family of such similar solution indexed by this parameter, and they solve this equation. Okay, you see in here I can add, as I said, the extra linear term, which allows me to have indeed a solution of the 1D cubic NLS. And you can see that this solution, of course, it's when t goes to 0, you are found the Dirac mass at 0 times a. And Gutierrez, Rivas, and Vega showed that the link between the coefficient you take here at the level of the NLS and the angle of the corner that your self-similar solution of the binormal flow generate is given by this complicated expression, but explicit. Okay, and then you have solution that are perturbation of this subsimilar solution. That's what we've done with Luis a few times ago. And this means at the level of NLS, this means that you want to perturb this particular solution of this equation and see what you can say about these perturbations. And convenient way to study is to do the pseudo transformation. So instead of looking in here what's happening at time 0, you're looking to the transformed equation and you're looking for a large time behavior when t goes to infinity, and you end up studying the equation of this type, which looks like the usual cubic NLS, but you have this extra factor in front that might cause you problem because, for instance, energy is not conserved, which is an important fact. Okay, and in experiments, this kind of self-similar solution are observed in the vortex for the delta wing planes. And the fact that they are observed means also that indeed it's true that this perturbation exists and they exhibit the same corner as the self-similar solution. And now, so we kind of finished studying the binormal flow with generating one corner. So the question is what's happening with several corners. So it's not just an academic question to want to see what's happening for n larger than 1. It is because also in experiments you can see this kind of vortex filaments. So vortex filament given, for instance, by a square that you can see the vortex behind the non-circular jets. Okay, jets that where air is exiting, for instance, through a square aperture. Okay, and at the mathematical level, there are some numerics done by Gerard and Smets, and also numerics and some conjectures that looks very reasonable in terms of the arguments that are given by De La Hoz and Vega. And of course, the problem here, so if you consider a regular polygon as a curve, means that it is as a curve, you can see it as an infinite curve, which all the angles are the same, right? Which means that at the level of NLS, you're supposed to understand the 1D cubic NLS with a sum of Dirac, which have all the same coefficient in order to get the same angle. Okay, which means that you are talking about the Dirac comb, and of course, the Dirac comb through the 1D cubic NLS, we don't know what it is because, of course, when you say cubic, you want to understand what will be the cubic power of deltas that we have. It's delicate. And but nevertheless, we know, for instance, what is the evolution of the Dirac comb by the 1D linear Schrödinger equation. And now it gets to what Nikolai explained to us. So this typically will you can write it in by using the Poisson summation formula. You can write it at an infinite sum of exponential, and you have an explicit expression of the evolution. And at rational time, you will find again a combination of Diracs. So you have a very nice but agitated behavior, which is called the Talbot effect. Okay. So in order to understand what's happening with precisely this kind of initial data and at the level of NLS or this kind of initial data at the level of the binormal flow, what we consider in the last year with Luis are polygonal line with maybe infinite number of corners, but whose corners are getting more and more close to pi. Even more than that, having curves that have whose tangent have a limit at plus and minus infinity. So which will mean eventually, just to fix idea, that we will consider combination, infinite combination of Diracs, but with coefficients that will be summable. Okay, and then we'll give solution in link to this combination of Dirac. So let's go. So this was the initial theorem that we managed to solve the problem. I will say, when I will, before the proofs, I will say in which sense we have a solution for the NLS for approaching a combination of Diracs. And then we have been able to transport the information at the level of the binormal flow and obtain indeed that if you take a polygonal line with with some condition on the way the angles all go to pi when the angle where you are looking to further and further angles. Then you can construct, you have a solution unique in the sense that you have uniqueness at the level of the NLS in the class of solution we are looking at. And they are smooth before the singularity time, and that time 0, you get these several corners, and then we are able also to continue the solution after the corners appear, and the solution becomes smooth again. And also, this is very nice, this solution captured the phenomena that were observed in numerics by Gerard Smets and De La Hoz, Vega, and also by Kumar. And typically, if you take, you can approach the polygon of square by taking 1,000,000 times a square and then complete to 2 lines to infinity. And also you can give examples of polygonal lines that will present a Talbot effect as observed in numerics, in the sense that at a rational time, you cannot expect, as for the numerics for the pure square, for instance, that you get again skew polygons because your solution will be smooth, but nevertheless you obtain at rational time that your curvature is almost null for segments, which means that you are almost flat, almost a segment, and it is very high at between the segments. So this means that you really have smooth, skewed polygonal line. Okay, so now we have this class of solution of the binormal flow, and it is within this class that we started to do some further investigation. And well, one of the things that typically in fluid mechanics is, I mean, it was an issue in some sense, is that we are in infinite energy. So if you took the kinetic energy of the binormal flow and also the interaction energy for the Schrödinger map, well, it is exactly the two quantities, either tangent derivative, either the binormal flow solution derivated in time. These models are precisely the curvature square. Okay. And then in here, well, you are in infinite energy setting, but nevertheless, we managed to get some quantity which eventually is, have some meaning in terms of fluid mechanics, which is preserved up to the time of formation of singularity. So what is this quantity? Because I'm insisting on it, because it's this that I will call the energy. So this quantity, it is that you consider the Fourier modes of the variation of the tangent derivative, and you look at frequencies that are in an interval of size 1, and you push this interval to integrate, and you push this interval to go to infinity. And this quantity is precisely conserved for before singularity time, and it is also well defined at the singularity time when the corners appear, and we can compute it explicitly, and it has a different value for the one that it has before singularity. And this is quite nice in the sense that this quantity is not anodyne. It has a meaning in the sense that the variation of the tangent vector, if you think about how the binormal flow is interpreted as a model for the dynamics of vortex filament is that the tangent vector, so is the tangent vector to the curve you consider of the binormal flow. But if you have in mind that your binormal flow curve is a vortex filament, the tangent has exactly the direction, the tangent is the direction of the vorticity. Okay, so we are looking at the high Fourier modes of the variation of the vorticity. Okay, and it is well known that the variation of the direction of vorticity is something important in fluid mechanics. And when roughly this starts varying too much, then singularity appear. Okay. And now it is, now I will get to today's result, which is what about the density of energy, meaning precisely this quantity, before integrating it. So we will show that pointwise, we'll manage to show, to see how pointwise this quantity blows up and at which location it blows up when you approach the singularity time t equals 0. So here is the statement. So for simplicity, we take just the two corners, okay, same angle, also for simplicity. And then what we know is the following. So this is at time, roughly at time of size 1 over n squared, you take n as large as you want. At time of size 1 over n squared, if you look at the frequency in the balls of this kind, so center here means that you are center at n squared, okay, so you are far away, you are at frequency of size n squared, then you are sure that you have a logarithmic growth in n for these Fourier modes. Okay, and well, in particular, as a consequence, we get that the supremum of the infinity norm of the Fourier mode is larger than log of t for all t between 0 and some constant. Okay, because all this interval, you can split it in intervals like this with n larger than n theta, and on each such interval, you have a place where you have at least grows log n, okay? So eventually your infinity norm is at least of this size. And moreover, we can control that outside these balls with radius a bit larger than this, we are sure that there is no growth, okay? So roughly you have, when you approach t goes to 0, you have places where you blow up logarithmically, and outside roughly outside this region you are not blowing at all, you are just bounded. Okay, so it is quite a clear picture that how it grows. Okay, so some remarks, and here I have to apologize if I'm missing references, because it has been a huge research, amount of research about these topics. What I can say about our result is that in here you have an integrable equation, okay, and we prove growth. Of course, not for the superlative norms, but, and maybe it's even better, I would say, with something which is directly connected with the notions which appear in fluid, which I mean the variation of the direction of the vorticity. So here are some of the Fourier mode growth framework studied before. So several are for non-integrable equations, and also you have some results for integrable equations, but the models are quite abstract. I mean, it's not clear that what is the link with fluid dynamics, for instance. Okay, and what is nice also is that the growth we get is so we said we have growth of the L infinity norm of the Fourier modes. So this is a critical Fourier-Lebesgue norm for the Schrödinger equation. And also, well, this is an extension. I presented the theorem for 2 corners, but it is valid for several corners. And for instance, you can take a billion of time the square and then just put at the end the 2 half lines. And then you will get something which kind of approaches the square evolution, for which numerics have been done by De La Hoz and Vega, precisely looking at Tx hat. Okay, so that was actually the beginning. They saw this numerically, that Tx hat has some logarithmic growth. And in here, we really prove it rigorously on these polygonal lines. Okay. Vladimir, how much time do I have left?
Valeria, 10 minutes are okay?
Yes. 10 minutes. Okay. Okay, thank you. So let's go. Well, then I go fast on the history. Well, I think you all know about this. It is just I wanted to underline the fact that for the 1D cubic NLS, the invariant space are h dot minus 1/2 and Fourier L infinity. So h1 h dot minus 1/2. The latest result is the one of Harold Griffiths, Kidip, and Vishan. But of course, eventually we don't know what's happening in here, right, in this space. But the point is that our solution will leave a borderline in this space, because there are solutions that are at the level of regularity of the Dirac mass. Okay, so at least we say something about solution living in a space where we don't know too much what's happening. Okay, so what are these solutions? Because I think this is nice for the Schrödinger study in general also. So what we find is the following. So you take the 1D cubic NLS, the classical one, okay, on the line. Okay, and what we prove is that given yourself a sequence of complex number that are summable in some sense, I mean, some amount of summability, then we get a solution for strictly positive time, okay, which is exactly has this ansatz with Rj, some sequence that when t goes to 0 in some weighted space, whatever goes to 0. So kind of forget about this. And roughly the solutions are a combination of the fundamental solution generated by x at x equal j with some coefficient and with some phase. Okay. And this phase precisely prevents to pass this, this function at the limit when t goes to 0. So except if in case all the modulus of the alpha j are the same, so that you can remove roughly this part, you don't recover the Dirac mass at t equals 0. Okay, so we are not solving the problem with the sum of Dirac mass. We are finding solution for t larger than 0 that when t goes to 0 are connected, look like modulated sums of Dirac masses. Okay, and the proof is not so complicated once you have the idea of this ansatz, which is due to Kita, which studied the subcritical case. Well, you plug this ansatz into the equation. And since you are here at the critical power, you will have some problems with some resonant terms, but you are in dimension 1 and things are not so complicated. So you solve the system on the coefficient by a fixed point argument, a classical one, and by integration by parts roughly. So a remark which is quite interesting, I think, is that, well, you have this problem of cubic NLS that you look what's happening when t goes to 0, right? And you have this class of particular kind of explicit solutions. If you use the pseudo-conformal transformation, which will send you this equation into this equation, so it is the classical 1D cubic NLS, but with a coefficient that depends on timing here. And pseudo-conformal transformation means that you reverse time, so you are looking when t is large. However, if you look at the ansatz, if you pass it through the pseudo-conformal transformation, you end up precisely with roughly the linear evolution of modes with these coefficients. Okay, and this coefficient, which are composed by all this part, when t goes to 0, meaning here the 1 over t goes to infinity, they are like alpha j times this logarithmic phase. You see, so in some sense, this solution here, when you pass them through the pseudo-conformal transformation, give you example of wave operators where on each mode you made a long range correction on each mode. You see, we are used to see wave operators with the long range correction in front of all the solution, but in here it's all the modes are modified differently, but all kind of the same log of t correction. Okay, so now I have 5 minutes more and time for proof. Okay, let's see about the growth of tx hat. Okay, so you take tx hat, and you know already from the construction that tx is real part of your Schrödinger solution times the normal vector. You take the Fourier, okay, and then the Schrödinger solution we found have a simple ansatz like this. Okay, we plug it, we express what the real part is, that is this plus the imaginary, and then what? And then we put everything we can aside, right? And we end up with the oscillatory integral. Okay, we complete to the square in here to have a square in the integral, and then we want to see whether or not this guy can have some logarithmic growth. So what we should do first is that we remove parts that eventually are negligible in terms of growth. Okay, we place ourselves for t less than n square. And then, for instance, in here, you want to do as usual. You want to get smallest. Remember, this guy is E1 plus I2 is a vector of modulus 2. So a priori, you cannot, if you put just modulus, you cannot be able to integrate. So you really have to use the oscillation of the phase. To use the oscillation of the phase, you want to remove the region where the phase vanishes. So you first remove some small boils of size enough that you don't want to get more error than you are allowed to. And then once you remove this part, you can do integration by parts, and the guy in here appears downstairs. Okay, and then you have to differentiate everything is aside. And well, when you differentiate nx from the construction, you know that it is minus u times the tangent vectors, and u again, you know that it is of this shape. So you replace typically in the first term, you put everything you can aside. So in here, you see that you have already two guys, because you are roughly now dealing with u squared in some sense. Once you have u here and you get an extra u from here. And then the quadratic phases then cancel, and you end up with a linear phase. So no problem, again, you do integration by parts, you remove a part that you can just upper bound roughly here this by a constant, and then you do integration by parts again, and you get this kind of general estimate that if t is less than roughly 1/n squared, the quantity you're looking at is, except some negligible terms, the leading term is this sum. Okay, so now what we will do is that we will look at frequencies such that in this sum, you see this coefficient a capital Lj, roughly they are the little alpha j. So if you have, for instance, just a few corners in this sum, you are allowed to take just a few j and r. And you can impose a size of psi such that typically, for instance, if you take a psi asymptotic statement, okay, you will obligatorily see in this sum only the j and r that are related by this, that are dephased by 2, okay? And then, well, you just have one term, typically if you restrict to 2 corners in this sum, since you can take only this, j and the j plus 2, okay, you will end up just with one term, which will be given by alpha minus 1, alpha 1, okay? And you have the rest that remains, and the rest that remains, then you will have to use a formal result that tells you how the tangent evolves as you approach the singularity time. We have a rate of convergence, which is explicit, and eventually we get that the quantity we are interested in at the good at the time and the location I put in the statement. The leading part is given by this integral, and now the tangent at time 0 is the curve at time 0 is a broken polygonal line with 2 corners. So then you know what this value at any x, and you can integrate, and then you integrate and you end up with a logarithmic growth, okay, which comes from from the integral of this guy. You integrate this guy at the region that starts at 1/n. That's why you get the logarithmic growth, okay. And then, well, you put conditions such that this is the leading term, okay, because you have this alpha here and you have to be a bit careful, but well, eventually you end up with the condition on t and such that in the frequency region of this type you get a logarithmic growth. Okay, so I'm done. 14 over 14. So thank you very much for your attention.
Thank you, Valeria, for the nice talk, and really talk full of interesting results. Let us have a brief possibilities for questions, observations, if you have.
May I ask one question to Valeria?
Yes,
Please.
yes.
Please.
Do you have in growth in EU infinity in Xi? Are there some other norms in which you can observe growth, like I don't know, AOP norms in Xi or whatever?
If some AOP norms are growing, it's asking Nikolai.
Maybe, I don't know. Is it really restricted to the EU infinity norm in Xi, the growth, or some
in L2 you don't have growth, for instance.
Yeah, that's clear for me. But
you said LP, P equals 2.
Interpolation.
No.
Interpolation is okay. No, not good.
No, it's the other way around. No, if we want the growth, no, we just look at the infinity.
Okay. And one small thing, two-dimensional case, the last thing you presented is 1D case. Do you plan to extend for 2D case?
I don't understand.
When you showed for 1D Schrödinger equation, the logarithmic growth,
Yes.
this is for 1D case, dimension 1.
Well, the passage from the binormal flow to the, I mean, the binormal flow gets to just 1D cubic NLS.
The model is for 1D, okay.
Yes. Then you can, well, you can look at this problem and look for a solution like this in higher dimension.
Yes.
But the issue will be that the resonance set is more complicated. So,
of course, yes. You have two-dimensional orthogonality. Yes. Okay, thank you.
You're welcome.
Other questions, observations from everywhere, internet or... Nicola is asking.
Ciao, Nicola.
So, just one question. When J goes to 0, it is uniformly J.
Rj goes to 0 in weighted spaces in little j.
Okay. Then another question. Sorry. So you construct examples of growing solution, right? But you expect some upper bounds, even much worse, maybe polynomial for a larger class of initial data.
For another class of initial data, I have
Larger.
I don't think so. I mean, larger class. You mean if you the thing is that even for the square evolution, so Pachi and Ruiz did numerics, and they find just logarithmic and growth, and the square, the pure square, is the worst as the term of regularity because it is having alpha j equals 1. I mean, you have no summability. You see, it's you're in a. So even numerically, even at the worst, largest, I mean, worst generalist type of solution, which is the Dirac combis or something where you don't have summability in alpha j, they see only the logarithmic growth, So.
Okay, so are there something else? Okay, so thank you again, Valeria, for for discussions and a nice talk.
Thank you very much for your attention. So bye.